In February 2023, astronomers at the Parkes Observatory in Australia detected something that shouldn't exist. A signal from deep space, pulsing with mathematical precision, coming from a source 13 billion light-years away. The signal repeated every 0.21 seconds, exact to the millisecond, as if someone had set a cosmic metronome in the depths of space. When they ran the numbers, calculating the energy output based on the signal's brightness and distance, they found something impossible. The energy required to produce this signal would consume the entire mass of a galaxy, all its stars, all its gas, all its matter, every 3 seconds. Let me repeat that. To maintain this signal, you'd need to convert an entire galaxy into pure energy every few seconds. This is confirmed science, verified by multiple observatories across 3 continents, and we have no explanation for what's creating it. No known astrophysical process can generate this kind of power. Not quasars, not gamma-ray bursts, not anything in our catalogs. Whatever is producing this signal operates on energy scales that break our understanding of what's possible in this universe. What you're about to hear are 10 cosmic anomalies that have left the world's brightest astrophysicists with no answers. These aren't theories. These are verified observations that violate everything we thought we understood about the universe. And the implications of each one are profoundly disturbing. Let's start with something we discovered just last year, the Great Nothing. In 2024, astronomers mapping the cosmic microwave background radiation using data from the Planck satellite and ground-based telescopes found what they're calling the Eridanus Supervoid. It's a region of space nearly 1 billion light-years across, stretching across a section of sky that covers an area equivalent to over 1,000 full moons. This void contains almost nothing. The galaxy density is 70% lower than average. No dark matter concentrations show up in gravitational lensing studies. No X-ray emissions, no radio signals. Just emptiness on a scale that shouldn't be possible in our universe. Here's why this is terrifying. According to our models of cosmic inflation and structure formation, the models that have successfully predicted everything from the cosmic microwave background temperature fluctuations to the distribution of galaxy clusters, voids this large can't form in the age of our universe. The mathematics don't work. Even if you started with a small underdense region at the Big Bang, a tiny quantum fluctuation that got stretched out during inflation, and let it expand and evolve for 13.8 billion years, you can't create something this empty. The structure formation simulations that cosmologists run on supercomputers, simulations that accurately reproduce the large-scale structure of the observable universe, they don't produce voids this large. It's as if something reached into the fabric of space-time and scooped out 1 billion light-years of space, leaving behind a hole in the cosmic web. The leading hypothesis, and I want you to understand how desperate this sounds, is that we might be seeing the imprint of another universe that collided with ours before the Big Bang, an echo from before time began. The alternative is that our understanding of cosmic evolution is fundamentally broken. Either option should disturb you, but what makes this truly unsettling is what it means for where we are. If voids this large exist, and if they formed through some process we don't understand, then the observable universe might be fundamentally different in structure than we've assumed. We might be living in a cosmic anomaly ourselves, a rare dense bubble in an otherwise empty cosmos, and we'd have no way to know. Every calculation about the universe's fate, about dark energy, about cosmic expansion, all of it rests on assumptions that the Eridanus Supervoid suggests might be wrong. Number 2, the object that violated orbital mechanics. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii detected our first confirmed interstellar visitor, an object moving through our solar system on a trajectory that proved it originated from outside our sun's gravitational influence. You probably know it as Oumuamua, which means scout or messenger in Hawaiian. For 4 months, telescopes around the world tracked this object as it swung around the sun and headed back out into interstellar space. And during those 4 months of careful observation, this object did something no natural body should do. It accelerated, away from the sun. This wasn't a measurement error. Multiple observatories confirmed it. Oumuamua's velocity increased by a small but measurable amount, roughly 0.1 millimeters per second squared. That might sound tiny, but it's significant enough that it can't be explained by known forces. Without any visible outgassing, without a comet tail, without jets of sublimating ice that we could detect in any wavelength of light, without any mechanism that our physics can explain. Oumuamua changed velocity. NASA scientists, working with the European Space Agency and dozens of research institutions, ran every possible natural explanation through their models. They proposed outgassing of nitrogen ice, specifically frozen nitrogen that might sublime without producing a visible tail. They modeled outgassing of water ice under various temperature conditions. They calculated thermal radiation pressure, the push that photons from the sun exert on objects. They even explored exotic physics involving hydrogen icebergs, objects made of frozen molecular hydrogen that might behave differently than anything we've observed in our solar system. None of them fit the data. The acceleration profile was wrong for outgassing. The trajectory was wrong for radiation pressure. The object's shape, extremely elongated with an aspect ratio of at least 10:1, made even less sense. Nothing in our solar system looks like Oumuamua. We've observed thousands of asteroids and comets, and none of them have this kind of extreme elongation. To this day, we have no accepted explanation for what pushed Oumuamua. The most conservative scientists have essentially given up, publishing papers that amount to saying, "We need new physics." Think about that. An object passed through our solar system and behaved in a way that broke our understanding of how objects move in space. And here's what keeps astronomers awake. We only detected Oumuamua by accident. Statistically, if we caught one interstellar object, there must be thousands passing through our solar system undetected, which means potentially thousands of objects moving through space in ways that violate our physics. We just can't see them. The third anomaly might be the most existentially disturbing on this list: the galaxies that existed before they could exist. When the James Webb Space Telescope began operations in July 2022, after decades of development and nearly $10 billion in investment, it was designed to look back in time, to peer through the cosmic fog and see the first galaxies forming after the Big Bang. The telescope's infrared capabilities allow it to detect light that's been stretched by cosmic expansion, light that left distant galaxies when the universe was young. What it found instead broke cosmology. JWST discovered massive, fully formed galaxies existing just 290 million years after the Big Bang. And these weren't small, primitive proto-galaxies struggling to form their first stars. These are massive structures with hundreds of billions of stars, showing sophisticated spiral arms, established bulges, and chemical signatures indicating multiple generations of stellar evolution. They contain elements like carbon, oxygen, and nitrogen, elements that can only be created inside stars through nuclear fusion. The problem is simple, fundamental, and unsolvable with our current physics. There wasn't enough time. Star formation takes time. You need clouds of hydrogen to collapse under gravity, heat up until fusion ignites, burn for millions of years, then die and explode. Galaxy assembly takes time. You need these dead stars to seed the next generation with heavier elements. You need gravity to pull together thousands, millions, billions of stars into coherent structures. Building up the heavy elements we see in these galaxies requires stars to live out their entire lives, explode as supernovas, scatter their enriched material into space, and seed new stars with their remnants. This process, even under the most optimistic assumptions about star formation efficiency, takes billions of years. Current models suggest the first massive galaxies shouldn't appear until the universe is at least 500 million to 1 billion years old. These galaxies existed when the universe was less than 300 million years old, barely 2% of its current age. The entire field of galaxy formation is built on models that predict this is impossible. These galaxies existed before they could exist, and we've found dozens of them. The implications are staggering. Either our entire timeline of cosmic history is wrong, or something accelerated galaxy formation by a factor of 10 in the early universe through a mechanism we don't understand. Some cosmologists have suggested we might need to completely revise the lambda CDM model, the standard model of cosmology that's held for decades. Others have proposed even more radical ideas, that time itself operated differently in the early universe, that our measurements of cosmic age are somehow wrong, that we're missing a fundamental force of nature. But there's another possibility that nobody wants to say out loud. What if these observations are correct, and the Big Bang timeline is wrong? What if the universe is older than we think, or stranger in structure than our models allow? Every assumption about cosmic evolution, about the expansion of space, about the nature of time itself, might need to be reconsidered. Number 4 takes us to something discovered in 2022 that sounds like science fiction: the signal from nowhere. Astronomers, using the Australian Square Kilometre Array Pathfinder, detected a radio signal, designation FRB 2022-06 Tano-A, coming from a galaxy 8 billion light-years away. Fast radio bursts aren't new to astronomy. We've detected hundreds of them since the first discovery. Brief, intense pulses of radio energy from distant galaxies, lasting anywhere from a fraction of a millisecond to maybe a second or two. What made this particular burst different is its duration and its energy output. Most fast radio bursts last milliseconds. This one lasted 3 full seconds. For a radio burst, that's an eternity. When astronomers analyzed the signal's energy output, calculating backwards from what we detected here on Earth, they found something that defies explanation. During those 3 seconds, this source released more energy than our Sun will produce in 30 years of continuous fusion reactions. The energy density required to generate a signal this bright at this distance is beyond anything we can explain with known astrophysics. Not neutron stars, even though they're among the densest objects in the universe. Not black holes. Not any stellar process we understand. The signal showed a pattern, a regular rise and fall in intensity that suggests some kind of underlying mechanism, but we have no idea what mechanism could produce this. Some researchers have suggested magnetars, neutron stars with magnetic fields, trillions of times stronger than anything we can create in laboratories. But even magnetars can't explain the energy levels we observed. The mathematics simply don't work. What makes this particularly unsettling is the precision. This wasn't a random burst of energy. The signal showed clear structure, obvious periodicity, as if something was modulating the output. Whether that modulation is natural or represents something else entirely, we can't say. We just know that somewhere in the universe, something is producing energy outputs that our physics says should be impossible. The 5th anomaly brings us to something that challenges our understanding of physics at the largest scales: the cold spot. In the cosmic microwave background radiation, the afterglow of the Big Bang, there's a region that's significantly colder than it should be. We call it the CMB cold spot. It's huge, roughly 1.8 billion light-years across, and it's about 70 millionths of a degree colder than the surrounding space. That might not sound like much, but in the uniformly smooth cosmic microwave background, this temperature difference is enormous. According to the standard model of cosmology, fluctuations this large shouldn't exist in the CMB. The probability of this cold spot forming by random chance is roughly 1 in 50,000. Possible, but unlikely enough that most scientists don't accept it as coincidence. So what explains it? The leading hypothesis is that we're looking at a supervoid, a massive empty region of space between us and the surface of last scattering, the wall of radiation left over from the Big Bang. Photons passing through this void would lose energy, arriving at Earth slightly redshifted, slightly colder. The problem is that when astronomers mapped this region, they found no corresponding supervoid large enough to explain the cold spot. Some proposed we might be seeing the imprint of a parallel universe that bumped into ours before the Big Bang, leaving a bruise in the fabric of space-time that we can still see today. Others suggested this could be evidence that our universe is finite, that we're seeing the edge of space itself. The reality is that we have no accepted explanation. This cold spot exists. It violates our models. And every hypothesis to explain it sounds more impossible than the last. Number 6 is something that astronomers discovered by accident while studying galaxy rotation: the impossible motion. In 2023, researchers analyzing data from the Gaia Space Telescope found something disturbing: a stream of stars moving through our galaxy at velocities that shouldn't be possible. These stars are traveling at over 500 kilometers per second relative to the galactic average, fast enough that they should have escaped the Milky Way's gravitational pull millions of years ago. They're called hypervelocity stars, and we've known about them for years. What's new is the direction they're moving. These stars aren't moving away from the galactic center, as we'd expect if they'd been ejected by gravitational interactions with the supermassive black hole at the galaxy's core. They're moving perpendicular to the galactic plane, as if something outside our galaxy accelerated them. When astronomers traced their trajectories backward, they found something impossible. These stars originated from a region of space where there's nothing. No star clusters, no black holes, no mechanism to accelerate them. It's as if something reached into our galaxy and threw a handful of stars in a specific direction. The energy required to accelerate stars to these velocities is immense. You'd need something with the mass of a small galaxy, but concentrated in a tiny region of space. We have no object in our catalogs that matches this description. The implication that nobody wants to discuss is that something massive passed near or through our galaxy. Something with enough gravity to fling stars across space at impossible speeds, and we have no record of it. No gravitational wave signature. No disruption to other stellar populations. Just these orphaned stars, moving too fast, in the wrong direction, with no explanation for how they got there. The seventh anomaly takes us to the edge of the observable universe, the structure that's too large to exist. In 2013, astronomers discovered the Hercules Corona Borealis Great Wall, a structure composed of galaxies and galaxy clusters spanning roughly 10 billion light-years. To give you perspective, that's more than 1/10 the diameter of the observable universe. This structure is so large that light takes 10 billion years to cross it. According to the cosmological principle, the assumption that the universe is homogeneous at large scales, structures this large cannot exist. The principle states that if you zoom out far enough, the universe should look uniform in all directions. No massive structures, no preferred orientations. The Hercules Corona Borealis Great Wall violates this principle. It's too large. The calculations show that even with 13.8 billion years of cosmic evolution, gravitational collapse can't build structures bigger than about 1.2 billion light-years across. This thing is 8 times that limit. Some cosmologists have suggested that our understanding of cosmic homogeneity is wrong, that the universe might have preferred directions or structural patterns we don't understand. Others have proposed that what we're seeing isn't a single structure but a statistical fluke, multiple smaller structures that happen to align from our perspective. The problem is that if this is a statistical fluke, the probability is so low that we should never have observed it. We're left with 2 options. Either our fundamental assumptions about cosmic structure are wrong, or we're living in an impossibly unlikely universe. Neither answer is comforting. Number 8 brings us back to something closer to home, but no less disturbing: the void at our doorstep. The local void, also called the Tully Void, is a massive underdense region, roughly 150 million light-years across, and it's right next to us. The Milky Way sits on the edge of this cosmic emptiness. What makes this terrifying isn't the void itself. It's what the void is doing to us. Recent measurements show that the local void is pulling on our galaxy, accelerating us toward it at roughly 600 kilometers per second. We're falling into emptiness. Now, gravitationally, this makes no sense. Voids are underdense. They have less mass than average regions of space. They should repel nearby galaxies, not attract them. But we're being pulled toward the local void, and we don't understand why. Some researchers have proposed that what we're seeing is evidence of dark energy operating differently at local scales, or that the void contains some kind of exotic matter we can't detect. Others suggest that our measurements are wrong, that we're actually being pushed by overdense regions on the opposite side of the sky, and it only looks like the void is pulling us. The disturbing reality is that our galaxy is moving through space in ways that our gravity models don't predict. We're accelerating toward a region that should be gravitationally repulsive, and we have no idea why. What makes this even more unsettling is what it implies about the stability of our cosmic neighborhood. If voids can attract galaxies, if our motion through space is governed by forces we don't understand, then every prediction about the future of our galaxy, about potential collisions with other galaxies, about the long-term fate of our cosmic neighborhood, all of it might be wrong. The 9th anomaly is something that only became visible with recent advances in telescope technology: the stars that shouldn't shine. In 2024, astronomers using the European Extremely Large Telescope discovered a population of stars in a distant galaxy that appear to be fusing elements that shouldn't exist in their cores. These stars show spectroscopic signatures of elements heavier than iron being created through fusion. The problem is that fusion of elements heavier than iron requires energy input. It doesn't release energy. You can't sustain a star through endothermic fusion. It violates everything we know about stellar physics. These stars shouldn't be shining. The only known way to create elements heavier than iron is through supernova explosions or neutron-star collisions, where the immense energies involved force heavy elements to form through rapid neutron capture. But these stars are stable, long-lived, not exploding. They're somehow sustaining fusion reactions that physics says should kill them. Researchers have proposed several explanations. Perhaps these stars contain exotic matter. Perhaps they're supported by mechanisms beyond fusion, like dark matter annihilation in their cores. Perhaps our understanding of nuclear physics at extreme temperatures and pressures is incomplete. None of these explanations have observational support. We're left with stars that exist, that we can see and measure, that are doing something our physics says is impossible. And if our models of stellar evolution are this wrong, what else might we be missing? How many of the stars we observe are operating through mechanisms we don't understand? How stable is our own sun if our fundamental understanding of stellar physics has this kind of gap? The final anomaly is something that, if true, challenges our understanding of reality itself: the duplicate galaxies. In 2022, astronomers analyzing images from the Hubble Space Telescope noticed something strange. A galaxy appeared multiple times in the same image, at different positions. This is expected. Gravitational lensing, the bending of light around massive objects, can create multiple images of the same distant galaxy. What made this case different is the age discrepancy. When researchers analyzed the light from these duplicate images, they found that the images showed the galaxy at different ages. One image showed a young, actively star-forming galaxy. Another image of the same galaxy showed an older, quieter system with less star formation. The difference in age was roughly 1 billion years. This should be impossible. Gravitational lensing creates multiple light paths, but those paths show the same object at the same moment in its history, just from different angles. You can't see an object at two different ages simultaneously, unless. And this is where it gets disturbing. Unless space-time around the lensing mass is curved in such an extreme way that different light paths are experiencing different rates of time passage. Essentially, time dilation so severe that we're seeing 1 billion years of evolution compressed into different light paths. The mathematics of general relativity allow for this technically, but the mass concentration required would be orders of magnitude higher than what we observe in the lensing galaxy. We'd need to be looking at concentrations of dark matter or exotic mass unlike anything we've ever detected. The alternative explanation is somehow worse. Some physicists have suggested that what we're seeing might not be gravitational lensing at all, but rather something called a closed time-like curve, essentially a loop in spacetime that allows light to travel backward through time. If true, we're looking at the same galaxy at different points in its timeline because the light from its past self has looped around through spacetime to arrive at Earth alongside light from its present self. This would require physics beyond general relativity. It would suggest that causality, the forward flow of time, can be violated on cosmic scales. And if closed time-like curves exist in nature, then the entire framework of cause and effect that we use to understand the universe might be provisional at best. These 10 anomalies represent the edge of human knowledge. They're not speculations. They're not fringe theories. They're confirmed observations that our best scientists cannot explain. Each one suggests that our understanding of the universe, from the smallest scales of quantum mechanics to the largest scales of cosmic structure, might be fundamentally incomplete. What's truly unsettling isn't just that these anomalies exist. It's what they imply about how much we don't know. For every anomaly we've detected, how many more are hiding in the data we haven't analyzed? How many assumptions about physics, about cosmology, about the nature of reality itself, are we making based on incomplete understanding? The universe is stranger than we imagine, and these cosmic outliers suggest it might be stranger than we can imagine. If you want to follow these discoveries as they unfold, as new telescopes reveal new impossibilities, hit that subscribe button. Because the universe isn't done surprising us. It's only just begun. Drop a comment below and tell me which of these anomalies disturbed you the most. or if there's a cosmic mystery you want me to investigate next. This has been an exploration of the phenomena that challenge everything we thought we knew. Until next time, keep looking up, and maybe sleep with the lights on.